Welcome to a fascinating exploration of the microfluidic scaling paradox, where the rules of fluid behavior completely flip at tiny scales. At the macro scale, fluids behave chaotically with turbulent swirls, but shrink down to microscale, and suddenly everything becomes calm and orderly, even under identical conditions. Let's start by understanding what this paradox actually means, and why it's so counterintuitive. At microscales, typically below 1 millimeter, completely different physical forces take over and dominate fluid behavior. Forces like surface tension and viscosity, which seem minor at large scales, become dominant giants at the microscale. Meanwhile, inertia and gravity, which control macroscale flows, become almost negligible at tiny scales. This diagram shows the dramatic shift in dominant forces. What matters at the macro scale becomes irrelevant at microscale, and vice versa. The Reynolds number is our key to understanding this paradox. It's a dimensionless number that predicts flow behavior. The Reynolds number equals density times velocity times characteristic length divided by dynamic viscosity, where ρ is the fluid density, v is the flow velocity, L is the characteristic length scale, and mu is the dynamic viscosity. Physically, Reynolds number represents the ratio of inertial forces to viscous forces in the fluid. Let me ask you a question. What does the Reynolds number actually tell us about how a fluid will behave? The answer is, when Reynolds number is less than 2,300, we get smooth laminar flow. When it's greater than 4,000, we get chaotic turbulent flow. This graph shows the flow regimes. Green is laminar, yellow is transition, and red is turbulent. The boundaries occur around Reynolds numbers of 2,300 and 4,000. Now we arrive at the heart of the paradox. Let me show you something truly counterintuitive. Let's consider water at 20 degrees Celsius as our working fluid for concrete examples. Water has a density of 1,000 kilograms per cubic meter and a dynamic viscosity of 0.001 Pascal seconds. For our macro example, imagine a large pipe with diameter of 0.1 meters or 10 centimeters at a velocity of just 0.023 meters per second, which is extremely slow. The Reynolds number equals 1,000 times 0.023 times 0.1 divided by 0.001, which gives us exactly 2,300. This Reynolds number of 2,300 puts us right at the edge where turbulence begins to appear at the macro scale. Now for our micro example, consider a microchannel with diameter of 0.0001 meters or 100 micrometers. To get the same Reynolds number, we need a velocity of 23 meters per second, which is incredibly fast, about 83 kilometers per hour. The Reynolds number equals 1,000 times 23 times 0.0001 divided by 0.001, which also gives us 2,300. Here's the critical question. Since both have the same Reynolds number of 2,300, should they behave identically? Classical fluid mechanics theory says yes, they should behave identically. But reality strongly says no. At macro scale with Reynolds 2,300, we see chaotic, turbulent swirls. At micro scale, with the same Reynolds number, we see perfectly straight laminar flow lines. Why does this paradox occur? The answer lies in how we measure and what we ignore. The Reynolds number formula assumes ideal conditions with smooth walls and no other effects. But at microscales, surface effects become absolutely enormous relative to the bulk fluid volume. The surface-to-volume ratio is proportional to 1 over the characteristic length. As L decreases, this ratio explodes. For a sphere, the surface area to volume ratio equals 3 divided by the radius. This means when radius shrinks by a factor of 1,000, the surface-to-volume ratio increases by a factor of 1,000. A millimeter sphere has a surface-to-volume ratio of 3. Shrink it to 1 micrometer and the ratio jumps to 3,000, a thousandfold increase. Surface tension, which we barely notice at large scales, becomes a dominant force at microscales. The surface tension force equals gamma, the surface tension coefficient, times the characteristic length. The gravitational force equals density times g times length cubed. The ratio of surface force to gravity force equals gamma divided by density times g times length squared. For water, the surface tension coefficient gamma equals 0.072 newtons per meter. At a length scale of 1 millimeter, the ratio of surface tension to gravity is about 7, so surface tension is 7 times stronger. But at 1 micrometer, this ratio explodes to 7,000. Surface tension is 7,000 times stronger than gravity. At the microscale, surface tension forces are like thick arrows pointing up, completely overwhelming the tiny gravitational force pointing down. Here's a powerful analogy to understand this paradox intuitively. Imagine a large lake where water moves gently across its surface, creating rolling waves and turbulent eddies. Now imagine a tiny, hair-thin capillary tube where water rushes through at high speed. Here's the question: which flow is more chaotic and turbulent? The answer is the lake, despite its much slower speed. The capillary flow remains smooth and laminar. The wide lake shows chaotic turbulent motion despite slow speeds, while the narrow capillary shows perfectly ordered laminar flow despite high speeds. The secret to understanding microscale flow lies in viscous boundary layers. At the walls of any channel, the fluid velocity must be exactly zero due to the no-slip boundary condition. The boundary layer thickness delta is proportional to the square root of viscosity times length, divided by density times velocity. In macroscale channels, this boundary layer is very thin compared to the total channel width, so most of the fluid can still develop turbulence. But in microchannels, the boundary layer grows so thick that it fills the entire channel. There's no room left for turbulence to develop. In a macrochannel, thin yellow boundary layers hug the walls with free space between. In a microchannel, the boundary layer fills everything, eliminating turbulence. Let's examine a real biological example: blood flow in capillaries. Human capillaries have diameters ranging from 5 to 10 micrometers, incredibly tiny vessels. Blood viscosity is approximately 0.004 Pascal seconds, about 4 times more viscous than water. Blood density is approximately 1060 kilograms per cubic meter, slightly denser than water. Blood flows through capillaries at about 0.001 meters per second, or 1 millimeter per second. The Reynolds number equals 1060 times 0.001 times 0.00001 divided by 0.004. This gives us a Reynolds number of just 0.00265, incredibly small. This Reynolds number represents extremely laminar flow, perfectly smooth and orderly, essential for efficient oxygen exchange. Blood cells, shown as yellow circles, flow smoothly through the capillary in perfectly laminar motion, with no turbulent mixing whatsoever. Another crucial aspect of the microscale paradox involves how substances mix and transport. At the macroscale, turbulent mixing is the dominant mechanism for transporting substances and mixing fluids. At the microscale, molecular diffusion becomes the primary transport mechanism, since turbulent mixing is absent. The Péclet number equals velocity times length divided by a diffusion coefficient, comparing convection to diffusion. D is the molecular diffusion coefficient, typically around 10 to the minus 9 square meters per second for small molecules in water. For a length scale of 100 micrometers and velocity of 0.01 meters per second. The Péclet number equals 0.01 times 0.0001 divided by 10 to the minus 9, which equals 1,000. This shows convection dominates over diffusion, but turbulent mixing isn't available, creating unique mixing challenges. Macroturbulent mixing rapidly disperses red particles everywhere. Micro-diffusive mixing slowly transports particles across streamlines, much slower but still effective at small scales. Understanding this paradox enables revolutionary applications in microfluidics. Lab-on-a-chip devices use microfluidic channels to perform complex medical tests on tiny blood samples, exploiting predictable laminar flow. Precise drug delivery systems use microfluidics to control medication release with incredible accuracy, down to individual cells. Microreactors for chemical synthesis exploit laminar flow to create precise reaction conditions impossible at larger scales. Inkjet printing relies on microfluidic principles to eject tiny, perfectly controlled droplets of ink. 4 revolutionary applications. Lab chips analyze samples, drug delivery targets cells, microreactors synthesize chemicals, and inkjets print precisely. Let's dive deeper into the mathematics that governs scaling behavior. Critical question: how exactly do different forces scale as we change the size of our system? Volume-based forces, like gravity and inertia, scale with length cubed. Surface-based forces like viscosity and pressure scale with length squared. Line forces like surface tension scale linearly with length. As the length scale decreases by a factor of 1,000, moving from millimeters to micrometers. Volume forces decrease by 10 to the 9th power, a billion-fold reduction. Surface forces decrease by 10 to the 6th power, a million-fold reduction. But line forces only decrease by 10 to the 3rd power, a thousandfold reduction. Different forces scale differently. Volume forces plummet fastest, surface forces are in the middle, and line forces decrease least, shown by arrow thickness. These scaling laws have profound implications for engineering design at different scales. You cannot simply scale down macro-scale devices to microscale and expect them to work the same way. Instead, you must completely redesign based on which physical phenomena dominate at your target scale. For example, micropumps cannot use rotating propellers like macropumps do, because viscosity dominates over inertia. Instead, microfluidic pumps use electroosmotic flow or carefully controlled pressure gradients. Propeller pumps with rotating blades fail at microscale due to viscosity, shown with red X. Pressure-driven flow works perfectly, shown with green arrows. Heat transfer also exhibits surprising scaling behavior at microscales. Heat conduction, which transfers through surfaces, scales with area, proportional to L squared. But heat generation in microelectronics scales with volume, proportional to L cubed. The ratio of cooling surface to heat generating volume is proportional to 1 over L. This shows that smaller devices have better heat dissipation per unit volume. Different forces scale differently. Volume forces plummet fastest, surface forces are in the middle, and line forces decrease least, shown by arrow thickness. To conclude, the microfluidic scaling paradox reveals the fundamental shift in physical laws as we move from macro to micro scales. The interplay between surface tension, viscosity, and inertia determines whether we see laminar or turbulent flow. Understanding this paradox is key to designing efficient and effective microfluidic systems, which have numerous applications in medicine, chemistry, and beyond. This is the microfluidic scaling paradox in essence, where understanding the shift in physical laws at the microscale enables the creation of innovative and efficient microfluidic systems.